This is part 2 of our seminars on how to make nearly anything in anticipation of our maker-themed startup weekend in a few weeks here at the Idea Foundry. This is a co-opted version of a seminar, actually a class, that Professor Neil Gershenfeld at MIT does called How to Make Almost Anything. And that's a 12-week class that teaches people a whole host of things. I've distilled this down into a 4, 5, or 6 hour kind of fire hose lecture from woodworking to welding to metal fabrication to vacuum forming to 2D design, 3D design, laser cutting, 3D printing, electronics, and more. This is just going to focus on the 2D design, 3D design, laser cutting, and 3D printing. We may do some Arduino at the end. That is, some electronics. The intention here is to give you an overview of what's possible. It's not intended to leave you as expert designers, expert fabricators, but rather to educate you about what resources we will make available during Startup Weekend, so that in advance you can think about how you design for these tools. So we're going to jump in here now. How do you make all the exciting things that we'd like to see people create during Startup Weekend? I'm going to start by just going over an overview of laser cutting. And if a picture is worth 1,000 words, then I think a video is worth 1,000,000. And I've taken the time to go through and curate some of the interesting YouTube videos I've found which demonstrate laser cutting, 2D design, 3D printing, 3D design, and more. You can see the original videos at these reference links. So here we have at the shop a Trotec as well as a full spectrum laser. These are about 3 foot by 4 foot laser cutting machines. And here I'm going to play a little video. You take a sheet of plywood or a sheet of plastic, you put it inside the machine, you level it, and then you execute your design on it. The designs can be created in 2D design software like Illustrator. We like Inkscape. Inkscape is a 2D open source free design tool. So Google Inkscape, download it. Oh, let me turn the music down off of this video here. There we go. So laser cutting, you can set the laser to cut all the way through your material wherever it sees a vector. Now a vector is really just a line, and that I think is the whole video there. But if you have a photograph, a JPEG for example, let me turn this music down too, then you can etch that image into the object as well. So here this person has created a 2D vector file where all of the vectors, all of those lines, represent through cuts in the material. And they've made this great Egyptian kind of design. But like I said, if you have an image or a JPEG, then that can raster or etch or engrave or burn into your material rather than cut all the way through. So if you have a photograph or if you have an interesting design, you can do that. I also really enjoy seeing three-dimensional shapes being constructed from two-dimensionally cut out parts. So we can see this light bulb frame here, we can see this whole bridge. We also see a really intricate iPhone case here too. I think this is great. So clearly this iPhone case, these through-cut holes were all machined with the laser cut through, but then all this textured engraved region was a JPEG or a raster image that told the laser to etch or machine into it instead of cut all the way through. And our experts will help you to know what settings to use to cut all the way through the material versus just etching images into it. And there's a whole industry of companies that sell products which are intended to be lasered. So you can just buy the blank for a trophy, for example, or keychains, and then use the laser to customize your design. I think this is one of the fastest ways to provide custom value, is to take an off-the-shelf mass-manufactured part and then add your own special component to it. And I think that's where our wheelhouse is. And then I also love clear acrylic or clear plastic parts. If you etch or engrave with the laser into that and put it on top of a light, the light diffracts around where those etch marks are and really catches it, really gives you a lot of interesting texture. That's the image on the left. And the image on the right here too, we can etch directly onto metal. So I'm surprised there aren't more custom service companies that will etch your phone case or your laptop case or your thermos or things like that. So that's a very quick overview of some 2D laser cutting, and now I'm going to go over some 3D printing. We have a number of 3D printing machines at the foundry, and they use a couple of different technologies. One of them is called Fused Deposition Modeling, or FDM. This is a fancy way of saying a hot glue gun controlled by computer. And here, this is a very high-resolution simulation of FDM 3D printing. That is the kind of hot glue gun for plastic. And let me turn this music down too. So here we see, well, you can't see a spool of plastic that is being fed into the extruder. The extruder then heats that plastic and deposits it in line-by-line fashion like this. So think of, as I said before, a hot glue gun controlled by a computer, or think of a baker's icing tube where they can just squeeze out material and build up something like a rose or words. So here we have a very zoomed-in simulation of this 3D printed component. So even though each of these layers would look essentially 2D, you can see the rounded shape of the actual filament being deposited. So you'll make layer by layer a 3D shape, and you can see here that you can build up a cone or build up a pyramid. I'd like to point out there's a problem, we call it the inverted pyramid problem, or inverted cone problem, where because each layer is being deposited on the previous layer, you have to have enough room underneath to stack the second layer up onto. So you can't build very, very square edge shapes or large layers on top of something without a structure beneath it. That's a little bit of a limitation of the FDM model. And here I'd like to show that these machines aren't just black boxes, magic boxes that will take your design and create it. They have a few flaws, they have a few quirks, so there's a bit of an art as well as science to creating these 3D shapes. And here we see someone who's building a reindeer. First they build the pads, then they start to build up the feet, and this is clearly time-lapse, it's clearly sped up. This whole reindeer might take 2, 3, maybe 4 hours to print. And I've skipped through the intermediate portions, but you can see there are a few little tags, extra ligands or little stragglers of plastic that didn't quite pinch off properly when the extruder went from layer to layer. Oops. And this is elucidated too when you see the antlers being built up. You can see they're dancing a little bit around. The extruder is actually pushing them up and down. So if you're trying to build something with really close tolerances, think press-fit, snap-together electronic enclosures or wearable tech, this is a challenge to make sure the tolerances are right, because as you can see, those antlers are being pushed around a little bit. So this is a great technology for artistic, organic components, jewelry, sculpture, things like this. If you want to make something that, that really presses together in a way where the tolerances are important, this is something we're trying to learn in-house. We're trying to make it easy so that rather than building 10 components and hoping one of them fits, we'll have some experience about exactly how to design to make sure that you can make a functional part. And again, we can see some of those stragglers, almost spiderweb, wispy little lines between the antlers that represent where the filament didn't quite pinch off. So some of this might require some post-sanding, some snipping of extra stuff off before you have a final part. Just emphasizing that these aren't magic machines that can make anything. They have their quirks and idiosyncrasies as well. There's another technology, however, called stereolithographic additive, SLA. This is a long word that describes tracing a laser through a liquid resin, and wherever the laser touches the liquid resin, it cures it or solidifies it. And here we have another kind of close-up example of how this technology works. Again, we have a computer simulation where a laser shines on actually a set of mirrors, and those mirrors are then angled and controlled by a computer to raster the laser across the liquid. And as each layer is being produced, the bed drops down and makes the next layer. Because this is being supported in liquid resin, you don't need support structure, support material. You can make shapes that have a very steep shoulder. Essentially, you don't have that inverted pyramid problem that you do with FDM, fused deposition modeling. This is an example of another of the machines we have at our shop.